In today's lecture, we will discuss the L'Hopital's rule. To begin with, let us consider two functions f of x and g of x, and these two functions are differentiable on an open interval a, b, and it contains the point x equals to c. Now suppose at that point x equals to c, when we take the limiting value of the function f of x over g of x, if we get something of the form 0 divided by 0 or infinity divided by infinity, then this is what we have is a indeterminate form, and in that case we can use the L'Hopital's rule, which is simply by first we take the derivative of both the numerator and the denominator, and then we apply the limiting value. To best understand this, let us consider the example. So let's say we have to obtain the limiting value of sine x over x. Now, if we substitute the value of x with 0, then we have sine 0 divided by 0. And sine 0 is simply 0. So 0 divided by 0, this gives us the indeterminate form. Indeterminate in the sense we cannot find out the answer to this value. That means the function simply blows up x equals to 0, or when it approaches 0. So what we do? We can apply the L'Hopital's rule. L'Hopital's rule will be simply, we consider the limit. So now what we'll do, we'll take the derivative of the numerator with respect to x, and we also take the derivative of the denominator with respect to x. So this will give us limit x approaching 0. The derivative of the sine function is the cosine function, and derivative of x with respect to x, that is 1. Now when we calculate the limit, this gives us the value cosine of 0, which is 1. So that means the limiting value of sine x over x, this is going to be 1 when x approaches 0. This is what we have been using so far. Using L'Hopital's rule, we can also obtain the same result. Let's try some more problems. So here we have the function x raised to the power of n minus a raised to the power of n divided by x minus a, and we want to obtain its limiting value when x approaches a. So we always have to begin by first calculating the value of this function at this limiting point. So that means we have a raised to the power of n minus a raised to the power of n divided by, in place of x we are replacing with a. So this gives us a indeterminate form, which is 0 over 0. So that means we should apply the L'Hopital's rule. So we have limit x approaching a. So we will begin by taking the derivative of the numerator with respect to x. Similarly, we also take the derivative of the denominator with respect to x. So let's find it out. So this will going to give us, we have limit x approaching a. So derivative of x raised to the power of n, we can use the power rule here. So this will be n times x raised to the power of n minus 1 minus derivative of a raised to the power of n, though that is simply 0 because a is a constant and so is the value n, divided by x minus a. So this is going to be 1. Now when we substitute the value of x with a, we get n times a raised to the power of n minus 1. So this is the limiting value of our given function, and a raised to the power of n minus 1. Let us go to the next problem. So we have the function natural log of 1 plus x divided by x, and we need to find its limiting value when x approaches 0. So let us begin. First thing first, let's substitute the value of x with 0. So we have log of 1 plus 0 divided by 0. In the numerator, we have log of 1, which is always 0. So this is giving us a indeterminate form, 0 over 0. So what should we do? We will use the L'Hopital's rule, and we need to take the derivative of the numerator. So the numerator is log of 1 plus x. Here we have to use the chain rule. So this will give us 1 over 1 plus x multiplied to derivative of 1 plus x with respect to x divided by derivative of x, which is simply 1. So this will be equals to limit x approaching 0. So we have 1 over 1 plus x, and derivative of 1 plus x is simply 1. Now when we use the limiting case when x goes to 0, this is simply going to give us the value 1. Hence, we can say that the limiting value of log of 1 plus x over x when x approaches 0 gives us the value 1. So we have the function x times e raised to the power of negative x. We need to find its limiting value when x approaches an extremely large number. So first, if we substitute a value with infinity, x with infinity, we have infinity times e raised to the power of negative infinity, which is equals to infinity divided by, so this is simply e raised to the power of infinity, and this is giving us the form infinity over infinity, which is an indeterminate form. So that means we can use the L'Hopital's rule. So the L'Hopital's rule will be limit x approaching infinity, but before that we have to rewrite our expression as x divided by e raised to the power of positive x. Now we'll apply the L'Hopital's rule. So derivative of x with respect to x is 1, and derivative of e raised to the power of x with respect to x, that is the function itself. And now when we apply the limit, we have 1 over e raised to the power of infinity. So this is going to be an extremely large number. So 1 divided by an extremely large number will give us a value very close to 0. So this is the limiting value of the function z, which is 0. So we want to find out the limiting value of cosec x minus cot x when x approaches 0. So let us begin. So first, we will substitute the value of cosec x, or x with 0. So we have cosec of 0 minus cotangent of 0. So cosec of 0 is infinity because it's 1 over sine 0. So 1 over 0 is infinity, minus, this is also infinity. We have infinity minus infinity. However, this really doesn't make any sense because we need either into 0 over 0 or infinity over infinity form. So that means we can rewrite our function as, let's rewrite it. We have x approaching 0. Cosec x will be 1 over sine x minus cotangent of x. So that's the ratio of the cosine function to that of the sine function. So this is limit x approaching 0. We have 1 minus cosine of x divided by sine x. Now when we substitute x with 0, so we have 1 minus cosine of 0 divided by sine 0. Cosine of 0 is 1 and sine 0 is 0. So that means we have 1 minus 1, which is 0 divided by 0. So this is an indeterminate form. Actually, infinity minus infinity, this is also referred to as an indeterminate form. But we wanted to make it look more obvious, 0 over 0 form. So that's why we had to do a little bit of manipulation here. Now let's apply the L'Hopital's rule. So we have limit x approaching 0. So we are going to apply the L'Hopital's rule to 1 minus cosine of x divided by sine x. So let's take the derivative with respect to x. We have 1 minus cosine of x divided by derivative with respect to x of sine x. So this will be equals to limit x approaching 0. So derivative with respect to x of 1, this is 0, minus derivative of cosine x, which is negative sine x. So this will become positive sine x, divided by derivative of sine function as the cosine function. Now when we take the limiting value of x, we have sine 0 over cosine of 0. So sine 0 is 0 and cosine 0 is 1. So 0 over 1, this was going to give us 0. So that means the limiting value of this particular function when x approaches 0 is 0. Let us do a final problem. So here we have a function of the form 1 plus 1 over x whole raised to the power of x, and we need to determine its limiting value when x approaches infinity. That means if we substitute the value of x with infinity, we have 1 plus 1 divided by infinity whole raised to the power of infinity. So here 1 over infinity, so 1 divided by an extremely large number means this is simply 0. So we have something of the form 1 raised to the power of infinity. So this is not exactly 1. This is an indeterminate form. So how shall we determine the limiting value of this particular function? What we will do here, we will assume let y is equals to 1 plus 1 over x whole raised to the power of x. Then we take the logarithm on both sides. So we have natural log of y is equals to natural log of 1 plus 1 over x whole raised to the power of x. So we will get natural log of y is equals to x times natural log of 1 plus 1 over x. Now what we'll do, we'll take the limit on both sides with x approaches infinity, natural log of y this is the same as taking the limit x going to infinity of x times natural log of 1 plus 1 over x. So this can be also rewritten as limit x approaching infinity. We have natural log of 1 plus 1 over x divided by 1 over x. Now this is actually a 0 over 0 form. That's because, let's look at it. If we substitute the value of x with infinity, a very large number, so in the numerator we will have log of 1. And in the denominator, 1 divided by infinity, which is a large number, will be 0. We know the log of 1 is 0. So this is an indeterminate form, 0 over 0. Now that we have an indeterminate form, what we can do? We can apply the L'Hopital's rule here. So let's apply the L'Hopital's rule. So that means we will need to take the derivative of both the numerator and the denominator with respect to x. So this will be natural log of 1 plus 1 over x divided by derivative with respect to x of 1 over x, which we can rewrite it as x raised to the power of negative 1. Right. So we have, let me write it down here, limit x approaching infinity, we have natural log of y, which is equals to limit x approaching infinity. So what is the derivative of the logarithmic function? So this is simply 1 divided by 1 plus 1 over x multiplied to derivative with respect to x of 1 plus 1 over x. Here we have used the chain rule. Divided by derivative of x raised to the power of negative 1. So this is simply negative x raised to the power of negative 2, which will give us, so we'll have limit x approaching infinity. So this, let's multiply both the numerator and the denominator with x. So this will give us x divided by x plus 1. And we have a negative x raised to the power of minus 2 in the denominator, which is simply negative x squared. Multiplied to, so derivative of 1 plus 1 over x. So this will be negative 1 over x squared. So these two terms goes away. And we are left with limit x approaching infinity, x divided by x plus 1. So what we'll do, we'll now divide both the numerator and the denominator with x. So this leaves us with 1 divided by 1 plus 1 over x. Now when we take the limit, this will be simply 1 divided by 1 plus 1 over an extremely large number which goes to 0. So the limiting value of y when x approaches infinity, so this is 1. So this is not y, this is natural log of y. Fine. That's what we are working with. We took the natural log. Well, we need to get rid of the natural log. So if we use the definition, then limit y when x approaches infinity, this will be e raised to the power of 1. So what we are doing here is, if we have natural log of a equals to b, then a will be simply equals to e raised to the power of b. So this is the definition that we have used here. Now what was y? For y we let 1 plus 1 over x whole raised to the power of x. And the limiting value of this particular function is e, the exponent e. So this is the limiting value.